Hello and welcome to this small lecture on discrete time signal processing. Now first begin with what are signals and what are different types of signals. Now, signal classification could be either multidimensional signals where we have a one-dimensional signal, a sine wave, a two-dimensional signal, an image, or a three-dimensional signal, a video. We could also have continuous time or discrete time signals. We use or we rather sample the continuous time signal to obtain the signals at discrete intervals of time. And also we have deterministic versus random signals. And for the random signals, to study them, we require a lot of probability theory. Here we will deal with continuous time and discrete time signals. So a comparison for you. A simple cos wave, we say xa of t, is a cos. Now I would pronounce this as, it is ohm, but I pronounce this as omega. For analog signals, we use a different frequency term, where this ohm is nothing but 2 pi capital F, where capital F is the frequency of the continuous time sinusoidal signal. They represent the analog frequencies. And therefore xa of t, we can write it also as a cos 2 pi ft plus theta. Correspondingly, in the discrete time domain, we use omega as 2 pi. Observe that we use small f here, okay? And therefore, omega and f correspond to the digital frequencies. For a discrete time sinusoidal signal, we would get x of n as equal to a cos 2 pi fn plus theta. So observe, from this continuous time signal, we would be getting this discrete time signal. In the next few slides, we will be explaining how this is possible and how this is done. So t is a continuous time instant, and n is a discrete time instant at which the signal is sampled for the continuous time. When we are using both continuous and discrete time descriptions in the frequency domain, we have to use different symbols. So here we have omega, ohm and f for analog frequencies, omega and f for the digital frequencies. Now, periodicity of discrete time sinusoids. A discrete time sinusoid is periodic only if its frequency f. Observe that I'm using frequency f, so here we are talking in terms of the digital discrete time signal. Therefore, x of n plus n, where n is the period, should be equal to x of n, the original signal. That means the signal should repeat itself after an interval of time n. Now, if you take a simple example of cos 2 pi fn plus theta, we would get it as cos 2 pi f into n plus theta. To check whether it is periodic or not. And we observe that this is possible only if 2 pi fn is equal to multiples of pi, integer multiples of pi. And this is possible only if f is equal to k by n. So this shows that if we take a discrete time signal, for it to be periodic, it should satisfy the relation f is equal to k upon n, where f should turn out to be an integer value. Now, how do we sample this continuous time signal? So again, we're dealing with the same signal. xa of t is a cos 2 pi ft plus theta. In order to sample it, we put the time interval t as n into capital T. So basically, what happens is, what you've got here is a switch. Okay, you have the analog signal coming in, and you have a switch, and you close the switch after every interval of time nt, where n will be going from 1, 2, and so on, and you would get x of n. So writing it down, we get x of n is equal to xa sampled after every interval of time nt equal to a cos 2 pi mt plus theta. Now this sampling, t is the sampling interval. And this sampling interval can also be written as 1 upon fs, where fs is the sampling frequency. So that you get xn is equal to a cos 2 pi fn divided by fs plus theta. So now what I would do is I would combine this capital F and fs together so that you can turn this relationship, capital F, that means the analog frequency divided by the sampling frequency, to get to the frequency in of the discrete signal. So this f is equal to f upon fs, giving us our expression for x of n as a cos 2 pi fn plus theta. So basically this is how we go from a continuous time signal to a discrete time signal. Now, what is the relation between the frequencies and the analog and digital domain? Now we know this relation f is equal to f upon fs, or small f is equal to analog frequency, continuous time frequency into t. So therefore, substituting, we also know that omega is in terms, ohm is in terms of capital F, omega is in terms of 2 pi f. Now, the frequency for omega we all know is radians. Because we are dealing in discrete time, and because we know that there are various samples involved, the unit of omega is radians per sample. So now, taking the values of f and capital F and substituting in this equation, we get omega upon 2 pi is equal to ohm t upon 2 pi, giving us a relation of omega is equal to ohm into t. So observe that the discrete time frequency is the linear multiple of an analog frequency, showing that it's very easy for you to take out to get the digital frequencies because of the linear manner of this expression. Now, what is aliasing? How can this aliasing occur? And why do we not want aliasing? Well, discrete time sinusoids whose frequencies are separated by an interval of 2 pi, which they are identical. So because of this identical nature, suppose you've got cos of omega 2 pi, omega plus 2 pi into n plus theta. For various values of n, you get identical frequencies. Now this happens just because of trigonometry. You see, cos of 2 pi plus theta and cos of 2 pi minus theta is cos theta, and similar nature occurs for sine. So basically, after every interval of 2 pi, you get the same signal back again. And also observe the nature of the angle theta. The angle theta is retained. Plus theta here is retained. Here, of course, it's minus theta, but we know cos of minus theta is cos theta. Same thing happens in the case of sine. Now, sine also has a difference in the negative in terms of a minus sign, but that can be always said that the signal is identical in magnitude, just negative in direction. So basically what happens is the aliasing occurs because of this nature. And why should this aliasing be a problem? Because you get identical samples every interval of time 2 pi. Okay. They are called aliasing because it's the same signal coming again and again. But why should they be avoided? For the simple reason that during reconstruction, they could be incorrectly substituted for one another. And when we go back to the continuous time signal, that would give us a wrong interpretation. So therefore, for k equals to 1, 2 and all integer values, periodicity occurs. Because of the periodicities, there is aliasing, which should be avoided. Now, what do we do with this aliasing signal? Let's go to the next slide. We have to observe what is called this concept of the principal alias. Okay. Now, take a waveform, say cos of 0.3 pi n. Now, the first value is 0.3 pi. You can't break up 0.3 pi further. So now let's take another expression, cos of 2 pi 0.3 pi n. So now for this, it can be broken up as cos of 2 pi n plus 0.3 pi n, right? Now, what you're happening is, after every interval of 2 pi, the signal 0.3 pi is repeating once again. So this 2.3 would be an alias of 0.3. Similar thing occurs, you see, it's an alias. Now, similar thing occurs for 1.7. And you get 2 pi n minus 0.3, which is also cos. So for one principal alias, you have so many different aliasing possibilities. So the first one here is 0.3 pi n is called as the principal alias, because this principal alias will always occur with omega less than pi. Now, this is required. Why did we introduce aliasing here? Because when we are thinking analog and digital frequencies, where do I sample these particular frequencies? So one thing is, I could sample between omega between 0 to 2 pi. just because of the mere periodicity of omega, but also we observe that the principal alias occurs less than pi. So if it occurs less than pi, I can take it as between minus pi to pi. And if I put this expression of omega here, I get f between, this is minus half to plus half, and similarly omega t is between minus pi to pi. So if you simplify this, you get the range of operation of the continuous time signal between minus fs by 2 and plus fs by 2, and the frequency f between minus half, the fundamental frequency. Why? Because the principal alias occurs in this particular frequency, and omega occurs between minus pi to pi. So therefore, when we are taking out discrete time samples from a continuous time samples, we have to see that the frequency is of f, capital F, of the analog time signal should be between minus fs by 2 and plus fs by 2, and omega should be minus pi and pi. So this is what would help us to extract the discrete time signal, or this would be one of the limitations or manner of extracting a discrete time signal from a continuous time signal. Thank you.